Welcome students, welcome to the next session of structural analysis 2. So in the previous classes we have went into the matrix methods of structural analysis and then we came into two methods. First one is a flexibility matrix method and the next one is stiffness matrix method. And each individually they are having their own names and their method of calculation. So in the flexibility matrix method, in the name itself we are saying, so flexibility matrix we will use, and also the forces are the main unknowns and they will use compatibility equations. That's why force method or flexibility matrix method or compatibility equation method. So everything will be coming for the flexibility matrix method. There the main unknowns are the forces. Now coming to the stiffness matrix method, which is our next method of analysis using matrix concept. Okay, so for analyzing any indeterminate structure using the matrix method, as I am having more number of unknowns when we are going for the multi-storied level structures, for analyzing such a type of multi-storied or more number of unknown type structures, the mathematical concept of matrices will be involved into our original condition and a number of equations can be solved at a time. Okay, due to the application of load at some point, its influence on this coordinate also you can observe in the same matrix. Okay, so many analysis can be done using the single matrix which is having 4 by 4 at a time. 4 equations can be solved like that. Okay, now in case of the stiffness matrix method, so as we have already said, in case of flexibility, forces are the unknowns. In case of the stiffness matrix, displacements are the main unknowns. And when you observe the word force or displacement, forces generally involves forces and moments. Displacements generally involve displacements as well as rotations. Okay, in generally we will call as forces and moments. Sorry, forces and displacements. Generally, the word force, it may involve moments as well as forces, and displacements, it may involve displacements as well as rotations. Okay, so in this way, the method, the stiffness matrix method is using stiffness matrix. Okay, so the stiffness matrix will be used in the stiffness matrix method, and also the main unknowns are the displacements, and also we will use the equilibrium equations. And firstly, we will go into what is the stiffness matrix method and what are the other names it is having also we will see. So the stiffness matrix method, in this method, the basic unknowns to be determined in the analysis are the displacement components of the various joint. Okay, so when you observe a truss member or this point, so this coordinate, so what are the displacement of this position, what is the displacement of this position, or what is the rotation at the fixed end. So everything will be calculated. These are the displacement coordinates. So the coordinates will be given for the displacements, and then hence the degree of kinematic indeterminacy or the degree of freedom we should be identified first. So the degree of kinematic indeterminacy or the degree of freedom, because as we have said, displacement is possible when it is free. When it is free to rotate, it will rotate. When it is free to translate, it will translate. So once you know how many degrees of freedom possible, those many displacements possible. So number of degrees of freedom means number of ways of displacements it can have, it can go. So when you know the kinematic indeterminacy or the degree of freedom of the particular joint or particular structured member, so once you know the degree of freedom, then you can calculate how many displacement coordinates you need to calculate. How many ways it is going, those many ways I need to calculate the displacements. Okay, so once you know the kinematic indeterminacy, then only I can finalize the how many displacement coordinates are available. Okay, next thing, coordinate number is assigned to each one of the unknown displacement component. Yes, so once knowing the coordinates, we should have to give the numbering so that one by one we can analyze. Okay, these basic unknowns are delta 1, delta 2, delta 3. So at the coordinate, some final displacement is possible. At the coordinate, the final displacement at coordinate 1, the final displacement at coordinate 2. Even though the forces are applied all over the structure, involving all the influence, okay, involving all the loads influence, finally at coordinate 1, what is the final displacement? Due to the application of all the loads on the structural system, at the coordinate 2, what is the final displacement? That is delta 2. Okay, so in this way delta n are the displacements are the coordinates in the directions 1, 2 and so on and respectively. Okay, to start with, the joint displacement in all the directions are restrained. Remember, there we are freeing, released structure we will generate. In case of flexibility matrix, released structure we will generate, and in the released direction we will apply the forces. Here we will restrain all the supports. Okay, to start the joint displacement, also in all the directions are restrained. So the complete joint restrainings are happening. Okay, in other words, we start the analysis with a restrained structure, their released structure. This is restrained. Stiffness matrix, restrained structure is the first step. Flexibility matrix, released structure is the first step. Now, let the forces developed due to the applied loads in the direct restrained structure in the coordinate directions be P1, P2, P3 and so on Pn. As I am restraining all the supports, so due to that restrainment, some forces, so resisting moments or reaction to the supports, all the things will be generated, right? So, those generated due to our restrained condition, the forces which are generated due to the restrained condition are P1, P2, P3 and so on, Pn. Determine the stiffness matrix of the structure by applying unit displacement at each end of the coordinate direction and find the forces developed. So, stiffness matrix. So, once to determine a stiffness matrix, what we should have to do? We should have to apply a unit displacement. There we have applied unit force. Unit forces are applied due to the force. What is the displacement we have calculated using conjugate beam method, right? So, using the force we have calculated what is the displacement or the rotation. If the force is a moment, what is the rotation generated? If the force is a load, what is the displacement generated? That we have calculated. Here I am applying unit displacement. Due to the application of unit displacement, what is the moment generated? Due to the application of unit rotation, what is the force developed or the moment developed? That we should have to calculate. Okay. So, to determine the stiffness matrix of the structure by applying unit displacement in each of the coordinate direction, then find the forces developed in that direction. We should have to calculate what is the quantity of the force generated due to the application. As I am giving a displacement, what is the corresponding force may generate? If I am allowing the body to sink, due to the sinking or due to this displacement, what is the moment generated at all the coordinates? So, due to the sinking, what is the moment generated here? Due to the sinking, what is the moment generated here? So, those things will be calculated. Or in previously, we will apply some force or moment, and what are the corresponding results in the form of slopes and deflections we will calculate. Here, in the reversal action, we will do. Let K be the stiffness matrix and delta be the displacement vector. Let the final forces be P. Okay. So, the stiffness matrix is indicated with K and the vector, displacement vector is indicated with delta, and also the forces are indicated as P. Then, from the principle of superposition and the equilibrium condition, the forces developed in the coordinate system will be written as P1 is equal to P1L plus K11 delta 1, P12 delta 2. So, what are the things here? Principle of superposition and equilibrium condition. So, due to the application of the external load, due to the application of the external load I am giving, due to the load, okay, due to load L, what is the force at coordinate 1? Due to the given load, due to the external load, what is the force developed? Okay, due to that external load, what is the force developed at coordinate 1? If that is a UDL, force means here moment also a force. Okay, so the moment generated at 1 due to the external load, moment generated due to the given load at 1. Okay, that is P1L. The load generated due to the given live load or the given external load. Okay, load applied due to the given external load at coordinate 1, and also K11 delta 1 at 1 due to delta 2. So, due to delta 1 displacement at 1, what is the force generated? Due to delta 2 displacement at delta 2 displacement at 2, due to the delta 2 displacement, what is the force developed at 1? Similarly, due to delta 3 displacement, what is the force developed at 1? Due to delta 4 displacement, what is the force developed at 1? Due to delta n displacement, what is the force developed at 1? Due to the displacement, what is the force developed that I am calculating? Due to the given load, what is the force developed? Due to the displacement, what is the force developed? Due to this displacement, what is the force developed? So, all these forces are finally developed at coordinate 1 only. Due to displacement at that point, the force developed at this level. Due to the displacement at this position, what is the force developed here? Due to the displacement in somewhere, what is the force developed? And also, due to the given external load, what is the force developed at this coordinate? And summation of all, finally, at coordinate 1, finally, the total force developed will be calculated. Similarly, for 2, due to the external, what is the force developed at 2? Due to the delta 1, what is the force developed at 2? Due to delta 2, what is the force developed at 1? At 2. Due to delta 3, what is the force developed at 2? So, summing up, all total force developed at 2 will be calculated, that is P2. And similarly, when you continue, due to the load, what is the force developed at nth coordinate? Due to the given load, what is the force developed at nth coordinate? And due to the displacement at 1, what is the force developed at nth coordinate? Due to the displacement at 2, what is the force developed at nth coordinate? So, everywhere nth coordinates output k and 1. So, in this way the equations can be drawn. After this, we know how to write the matrix equation. So, this will be like a vertical vector, force vector P, and then I can indicate it as PL, load vector, okay, load corresponding force vector, force corresponding to the loads, okay, PL, and then K, stiffness matrix, and delta, displacement vector, okay. So, keeping K and delta as it is, we will shift the P at the PL that way and P minus PL. So, K times delta L is equal to P minus PL, okay. So, in this way, we have got the next equation. Solving the stiffness equation. What is the stiffness equation? K times delta is equal to P minus PL. So, solving the stiffness equation, the displacements in all the coordinate directions can be calculated. So, the displacements in, so once you know the stiffness matrix, this P minus PL will be known values and then the displacements will be calculated. So, solving the stiffness equation and displacements in all the coordinates can be found. Using the equilibrium equation, P1 is equal to P1L plus sigma j is equal to 1 to n k I j delta I. All the required forces can be calculated. So, due to at coordinate 1, total load at coordinate 1 is equal to, load developed due to external load, force developed due to external load, acting, and force developed at 1, due to the external load, and then force developed at 1 due to displacement at 1, force developed at 2 due to displacement at 1. Similarly, in all the conditions, we will sum up and we can calculate the corresponding force answers also. Okay, so in this way, we can evaluate the stiffness matrix analysis. Okay, and as we have already said, it is having 3 names. The first one is stiffness matrix method. So, in the case of stiffness matrix method, I am using the stiffness matrix here, K. Matrix K I am using, so stiffness matrix method. And then displacement method. Since the displacements are the basic unknowns, I am giving unit displacement, the corresponding force and calculating. So, in indirect way, final output is, after knowing the stiffness matrix, the displacement vector is the final output for me. So, the displacement matrix or the displacements or the unknowns will be calculated as the final outputs. That's why displacement method. And then equilibrium method. Since the equilibrium equations, as it is causing some sinking and it is causing some movement. So sinking is causing some movement. So in this way equilibrium condition is maintained. So those equilibrium conditions I am using for generating the stiffness matrix. Okay. The next thing is step-by-step procedure for the stiffness matrix method for the structural approach. Okay. Now we should have to determine the degree of kinematic indeterminacy. As we have already said, once you know the degree of kinematic indeterminacy or degree of freedom only, once how many ways of freedom possible, you should have to calculate. So once you know how many ways degrees of freedom is there, then you can think, so in these ways I need to calculate the displacements. So degrees of freedom or degree of kinematic indeterminacy n will be calculated and then assign the coordinate numbers to the unknown displacements. As we have already said, degree of freedom is there. So in the way I need to calculate the displacement. So for those unknown displacement, I should have to give the coordinate number 1, 2, 3, 4 like that. Whether it is a displacement or it is a rotation, in a way I have to give. And then impose the restraints in all the directions to get a fully restrained structure. Whatever is the support condition, we will make each and every support as a fixed end. Restraining, complete restraining even to the intermediate supports. Not only at the ends, but also to the intermediate joints we will give restrained condition or the fixed condition. And then determine the forces developed in each of the coordinate in the fully restrained structure, which is called as PL. Okay. So load developed for the each restrained structure. Okay. Loads are the forces generated. So in case of a fixed beam, what are the corresponding support moments? So that support moment matrix is the load vector. Okay. PL, not a load vector, that is PL indication for the fully restrained structure. That is the load generated or the force generated, PL. The next thing, determine the stiffness matrix K by giving unit displacement to the restrained structure in each of the coordinate direction and find the forces developed in the coordinate directions. Okay, so determine the stiffness matrix. How we should have to calculate the stiffness matrix? So after keeping the structure restrained, then calculating the PL due to load, what is the force, that answers you calculate. And then now at the coordinate applying 1 unit displacement. Applying 1 unit displacement, you should have to calculate the corresponding K, stiffness terms of the particular force. Okay, displacement of the restrained structure in each of the coordinate direction and then find the forces developed in that coordinate direction. Okay, force developed in the coordinate direction due to the given unit displacement. When I am giving unit displacement, what is the force developed that I should have to calculate. For this only structures approach is explained in the text. Okay. And observing the final forces, what we have said, stiffness matrix we have calculated. Stiffness matrix means for the unit displacement, how much force developed. So that is the stiffness matrix. Okay. Observing the final forces in the various coordinate directions, note the final forces P. And then from and solve the equation of the stiffness K delta L is equal to P minus PL and to get the displacements in the coordinate direction. To get the displacement in the coordinate direction, calculate the member forces using these joint displacements. So each member will have some member forces. Those member forces we will calculate using joint displacements. Right? So in this way the analysis or the method will be done in case of the stiffness matrix. So firstly, kinematic indeterminacy. What is the kinematic indeterminacy? We should have to determine. And then coordinate numbering to the unknown displacements. And then making the structure as a restrained structure. Then determine the forces applying for the restraint structure. So what is the force at the coordinates using the restraint structure? And then stiffness matrix development using unit displacement application at the coordinates. And then for this structure we are going, and finally observing the final forces, we will calculate P. And using the formula P and knowing PL and K, we need to calculate delta, the corresponding displacement coordinates in the directions, and finally calculate the member forces using the displacement. Okay, in this way we are completing the stiffness matrix method. Okay, how we are developing a numerical, simply observing a continuous wave, we will go through that problem. Thank you. We will continue the example in the next class.